So this is our last unit. It's a fairly short unit. What we're doing is some additional techniques of integration that we didn't do when we did integrals earlier, simply because we were trying to keep it as straightforward as possible. These just add on, um, an additional degree of difficulty. And then we'll also look at a topic that has been on the AP exam for a while, but it was never tested for a really long time. And then suddenly they decided, oh, we should start testing this. So I wanted to make sure that we went over it as well. So today we're going to look at two different cases where in order to uh, find an antiderivative, you have to do a little more work than we've done before. So the first one is with rational functions. If you have a rational function, r of x is equal to n of x over d of x. Bonus points if you can tell me why I called them n of x and d of x. It wasn't just for grins. There we go. Where n of x and d of x are both polynomial functions, and the degree of n of x is greater than or equal to the degree of d of x. The integral of r of x should first be simplified by use of long division. Yes, and I know for some of you, long division of polynomials is not your favorite thing. I'd never found it to be all that difficult. It's just like long division of numbers. I know that you may have learned synthetic division, which is fine. It'll work on this one. It isn't going to work on this one. So you might as well just use long division all the time. So here we notice that the degree of the numerator is exactly the same as the degree of the denominator. These are both a first degree polynomial. So before we do anything else, we're going to jump in and do a long division to simplify this. So we'll divide x plus 5 into x plus 2. X goes into x one time. I multiply the 1 times the x plus 5, and I get x plus 5. And I subtract, just like you would do in long division. So I've got 2 minus 5 is negative 3. So my integral now becomes the integral of 1, that's this whole number that we got here, plus a negative 3 over x plus 5, all dx. Remember, the remainder goes over what you're dividing by. So now we'll just take the antiderivative of this. So the antiderivative of 1 with respect to x is x. And the antiderivative of negative 3 over x plus 5. You recognize that?
Natural log x plus 5.
Almost. Left off one important little bit. Absolute value of x plus 5. Remember, because natural log is not defined for 0 or negative values, we have to put on that absolute value sign. Once you've done the long division on this particular one, it's pretty easy. The antiderivative is not difficult, but you could stare at this all day and not figure out that this was its antiderivative. Okay, now, as always, I tell people, okay, you should be able to, and I'm not suggesting you spend any time doing this, but you should be able to, once you found an antiderivative, check it by taking the derivative. So you don't need to copy this at all, but if you take the derivative with respect to x of x minus 3 natural log absolute value of x plus 5 plus a constant, we're going to get, hang on a second, put in one too many absolute value bars. We're going to get 1 minus 3 over x plus 5 plus 0, which is x plus 5 over x plus 5 minus 3 over x plus 5, which indeed is x plus 2 over x plus 5. So we'll also do this sometimes when we have a higher power in the denominator, We usually don't actually get over second power because it gets into a topic that we have not done and we will not do because it's a BC only topic called partial fractions. But here again, notice that the degree of the numerator is higher than the degree of the denominator this time. Also notice that this is a definite integral. What I do in most cases on these, because you're doing bits and pieces of it at a time, is I'll do the indefinite integral and then I'll evaluate it later. So again, we'll do the long division, x squared plus, you may or may not remember that you need to fill in any missing powers. So x squared plus 0x plus 1 divided into, and here there are no missing powers here. And before I go on and start performing this, sometimes students are like, see, it's not just like long division. And I'm like, yes, it is. This is like 201. You got to have the 0 in for the tens place. You got to have the 0 in for the x term that is between the x squared term and the constant term. So again, we'll divide x squared into 2x cubed goes 2x times. Multiply, we get 2x cubed plus 0x squared plus 2x. When we subtract, we get negative x squared plus 0x, and I'm going to go ahead and bring down the next term, plus 2. So now I'll do the division again. X squared into negative x squared is negative 1. So I'm going to have negative x squared plus 0x minus 1, and I'm going to subtract that. When we subtract, we end up with a remainder of 3. So we've got the integral, and again, I'll just drop the definite part for now, of 2x minus 1 plus 3 over x squared plus 1 dx. And you know what? I'm going to be able to do that all at once. I'm going to go ahead and put the limits of integration back in. I was thinking this is one. Occasionally, you have to do more work on this other part, and when you do, it's easier if you don't have to remember, oh yeah, which parts have I substituted in the 0 and 1 in, and which parts have I not. But here it's not a big deal. So antiderivatives, we'll have x squared minus x plus, do you recognize this antiderivative?
Tangent inverse.
Yeah. So that'd be 3 tangent inverse of x. And we want to evaluate all of this from 0 to 1. So it's going to be 1 minus 1 plus 3 times tangent inverse of x. Where is tangent equal to 1? Pi over 4. So the tangent inverse of 1 is pi over 4. Minus, when I substitute in 0, I've got 0 minus 0 plus the tangent inverse of 0. Where is tangent equal to 0?
0.
At 0, yeah. So this is 0. It turns out that all those are 0. Always check that. Just because the lower limit is 0 doesn't mean that the second half of the evaluation part is going to be completely 0. So this is just 3 pi over 4. So again, after doing the long division, they're usually not terribly difficult to take the antiderivative of. All right, so that's one type of problem where you have a rational function and the degree of the numerator is either equal to or greater than the degree of the denominator. If so, do long division first, and then it shouldn't be too bad. Now, the second part goes back to when we did our unit on U substitution. There's a lot of times that you could do without doing the U substitution, where you could just undo the chain rule. And once upon a time, not all that long ago, every integral on the AP exam was one where you didn't have to do U substitution. You could, and sometimes it made it easier, but you never had to. At some point, someone pointed out to them, probably one of the college people, that yeah, we expect them to be able to use substitution for things where you have to use U substitution. And the question becomes, well, how do you recognize it's going to be something where you have to use U substitution? Which is a fair point. It's almost always a composite function. So like the square root of x plus 3, that's a composite function, multiplied by something that is related to what's the inner part, but isn't the derivative of the inner part, right? When we looked for substitution before, you don't need to write this, but we looked for things like, okay, what if I had sine of x squared times 2x dx? We wanted a composite function, and we wanted the derivative of the inside function to be somewhere multiplied times that. Well, what we're showing here is it doesn't have to be the derivative, it just has to be related to the inside part. So let's take a look at how we're going to do this. Oops, missed it. So I would first rewrite this as the integral of x plus 3 raised to the 1/2 power times x dx. I'm just, again, just like we did with U substitution, I think most of us are more comfortable if the composite function comes first and then whatever else comes last. Just like we did with U substitution, we're going to let U be equal to the inside part. So U is going to be equal to x plus 3. Just like we did with U substitution, we're going to take the derivative, so du is going to be equal to dx. Unlike U substitution, you got one more step at this point. Because we've accounted for the dx, it's going to be replaced with du, and we've accounted for the x plus 3 to the 1/2, that's going to be replaced with u to the 1/2, but we haven't accounted for this variable here. Typically what we have to do is solve our u statement for x. Solving that for x just involves subtracting 3 from both sides. So I've got u minus 3 is equal to x. And now I know what I can put in the place of x. So we'll have the integral of u to the 1/2 times, in place of the x, I'm going to put u minus 3, and in place of the dx, we'll put a du. Now, there is no product rule in anti-differentiation, so we have no choice but to multiply that out before we try and take the antiderivative. So I've got u to the 1/2 times u. What will that be equal to?
U. No, to the 3/2.
U to the 3/2. Because it's u to the 1/2 times u to the first, and we add the exponents. Then minus 3u to the 1/2, all du. So now we take the antiderivative. That's going to be 2/5 of u to the 5/2 minus 3 times 2/3 of u to the 3/2 plus a constant. So here the 3 will cancel the denominator on the 2/3. I also notice, and if this appears on the AP exam, it's likely to be a multiple choice question. If it's a multiple choice question, they're likely to, but not necessarily required to, factor this. Notice I can factor a 2 out of both terms, and I can also factor a u to the 3/2 out of both terms. So I'll have 2u to the 3/2 times 1/5 of, when I factor u to the 3/2 out of u to the 5/2, I'm left with u to the 2/2. I'm just left with u minus, well, what's left here? Just 1. And that's important that it's 1. Students sometimes, a fairly common mistake is, well, that's all gone, so it's a 0. But I divided it out. I didn't subtract it out, so it's a 1. And then all that's left to do is put this back into terms of x. So it'd be 2 times x plus 3 to the 3/2 power times 1/5 of x plus 3 minus 1, all plus c. At that point, if it's a multiple choice question, they are likely to go ahead and distribute this 1/5 and gather like terms. It's a little bit simpler to look at. So 2 times x plus 3 to the 3/2 times 1/5 x minus 2/5, because I'm going to have 3/5 minus 1 is negative 2/5, all plus c. Again, it's very much not obvious that this would have been your answer. All right, let's try this one and see what we can do with it. I don't remember this one. I'm going to have to do this and see what happens. I'm going to rewrite it as 2 plus the square root of x to the negative 1 power dx. Not real happy about this. I'm going to go ahead and try it. I may have to find my notes someplace and go, how in the world did I do that? So I'm going to let u be equal to 2 plus x to the 1/2. Then du is going to be equal to 1/2 x to the negative 1/2 dx. And while the x to the negative 1/2 doesn't, I mean, the 1/2 doesn't really trouble me. I could multiply both sides by 2 to get rid of that. I can't move this over here because then I'd have an x and a du over here, and I don't want to have mixed variables. I'm like, okay, so what in the world am I supposed to do here? All right, well, I'm going to go ahead and multiply by 2. So 2 du is equal to x to the negative 1/2 dx. They're like, well, that's not great because I don't have an x to the negative 1/2 dx, right? I don't have anything here. Well, here's what I'm going to do. I'm going to solve this for x to the negative 1/2. So I'm going to subtract 2 from both sides. So I've got u minus 2 is equal to x to the positive 1/2 power, right? take the reciprocal of both sides. 1 over u minus 2 is equal to 1 over x to the 1/2, which is x to the negative 1/2. So then that means that x to the negative 1/2 dx, I can replace the x to the negative 1/2 with 1 over u minus 2. So I'll have 2 du is equal to 1 over u minus 2 times dx. You're like, well, that's not what I have. Okay, multiply both sides by u minus 2. So the quantity 2u minus 4 du is equal to dx. Now I can replace everything. So the 2 plus square root of x, I'm going to replace with u. So this is going to be the integral of u to the negative 1 times dx. I'm going to replace with 2u minus 4 du. Just like with the previous problem, I must multiply this out because there is no product rule for anti-differentiation. U to the negative 1 times 2u is what? 2. Yeah, those cancel out rather nicely. Minus 4u to the negative 1 du. So taking the antiderivative, this will be 2u minus 4. What's the antiderivative of u to the negative 1? Again, close. There we go. Natural log of the absolute value of u. We're actually going to find in just a moment that we can drop that, but you don't want to leave it off at the beginning. So u is equal to 2 plus x to the 1/2. So I'm going to replace every u with x to the 1/2. So this will be 2 times 2 plus the square root of x minus 4 natural log of the absolute value of 2 plus the square root of x, all plus c. It's not necessary, but again, if this is a multiple choice question, they may do various simplification. Distributing the 2, we get 4 plus 2 square root of x minus 4 natural log. Since the square root of x is always a positive quantity, adding it to 2 is always a positive quantity also, so I can drop the absolute value. So these problems always involve a pretty good bit of algebraic manipulation. Once you have manipulated it, the antiderivative is usually pretty straightforward. But it's that work at the beginning that's a lot. All right, let's take a look at this last one. I'm not going to take the time to rewrite it. I could rewrite it so that the composite is first, but I know I'm going to let u be equal to 3x plus 2. Then du is going to be 3 dx. And I may need to move the 3 in a minute. I'm not going to worry about it just yet, but I am worried about this 4x. Because I don't have anything to replace it. So I'm going to solve this 4x. So it'll be, I'll subtract 2 and divide by 3, so it'll be u minus 2 over 3 is equal to x. And if you want to take the time to write it as, 4x, this would be 4/3 of u minus 2 is equal to 4x. And if you want to go ahead and get dx by itself, this now would be 1/3 du is equal to dx. So now my integral will be the integral of the 4x is replaced by 4/3 of u minus 2. The 3x plus 2 to the 17th is just u to the 17th. And the dx is 1/3 du. As in all of these u sub required problems, I got to multiply this out. I'll go ahead and factor out the constants. So I'll have 4/9 of the integral distributing the u to the 17th. I'll have u to the 18th minus 2u to the 17th du. So this is 4/9 of 1/19 u to the 19th minus 2/18 u to the 18th plus c. I can factor out a u to the 18th, so I'll have 4/9 u to the 18th times u over 19 minus the 2/18 reduces to 1/9 plus c. And then we'll go ahead and replace the u with the 3x plus 2. So this is 4/9 of 3x plus 2 to the 18th times 3x plus 2 over 19 minus 1/9 plus c. And this one's sufficiently ugly to where, could you clean up what's inside this second set of parentheses some? Yeah, you could make it 3/19 x plus 2/19 minus 1/9, get a common denominator, add those together. It's just kind of ugly. So you should practice, simplify them as much as you can. But I'm also going to say sometimes it's just really, really ugly. I'm going to go ahead and do it just for completion's sake. So this will be 3/19 x. I've got 2/19 minus 1/9 is negative 1. Oh, wait a minute. No, that's 18 minus 19. Sorry, my fault. That'll be 18 minus 19 is negative 37 over 171 plus c. By the way, there is another way to solve this one. I don't recommend doing it, but you could expand the 3x plus 2 to the 17th and then distribute the 4x and then take the derivative, the antiderivative term by term. The antiderivative would be simpler. Raising that to the 17th would take a while. And then you have to distribute the 4x on top of that. Lots of places to make mistakes. Okay, any other questions?